Okay, welcome back. It's my pleasure to introduce Cuipo Jiang from Shanghai. She's going to speak about cohomological varieties of vertex operator algebras.
Okay, thank you. I can start now, right? Oh, okay, so first let me thank Professor Andrew Linshaw for his invitation to take part in this workshop online and to give a talk. My talk today is a joint work with Antoine, Caradot, and Zongzhu. So now let me give a brief to talk about briefly the motivation of this work. So first, we can look at this question from the point of view of VOA. So we know that given a vertex operator algebra or vertex algebra, so Zhu has introduced the C2 Zhu algebra, and from the point of view of geometrical point of view, so Cohomologically introduces the associative variety of a vertex operator algebra, and he proved that if VOA is finitely strongly generated, then it is C2 cofinite if and only if the associated variety is a point. So it gives a geometric characterization of the C2 cofiniteness of VOA. So it's very nice. So on the other hand, so we know that for C2 cofinite VOAs, their C2 Zhu algebra can be very different. So some of them are large, some of them are small. So we just think about that if we could find something that which is some kind of due to the associative variety of VOA to characterize at least in part the difference of the C2 Zhu algebras. So another motivation comes from the Kazoo duality. So recall that a ring A is called a Kazoo ring if A is an ungraded ring. Well, A0 is a semi-simple ring, and the A module A0, this A0 has a projective resolution by graded modules Pn. So on the mild finiteness condition, there is a well-defined Kazoo dual ring, and the double Kazoo dual is itself. So for example, so the symmetric algebra of the finite dimensional space and the exterior algebra of its dual space are Kazoo algebra and the Kazoo dual. So from this point of view, we want to find something that it is in some way an analog of Kazoo dual of the associative variety of a VOA. So the motivation is simple. So now let me give some result or notation. So let V be a vertex algebra. Then and the C2V is linearly spanned by such elements U minus 2V. Then we have a quotient space. So this, oh, sorry. So this RV has a Poisson algebra structure introduced by Zhu. So with the following this, okay. And then this RV is usually called the C2 Zhu algebra of V, and it was introduced yesterday by Toyoki. So V is called the C2 cofinite if this RV is a finite dimensional. Then so because RV is a Poisson algebra, so we can consider its scheme or maximum ideal scheme. So the associative variety of this is defined by Cohomological as the associative variety of V this. And he defined that a vertex algebra V is called the least if the associative variety is just a point. So then, sorry. Then, so usually consider the finitely strongly generated vertex algebra. So a vertex algebra is called finitely strongly generated if it is linearly spanned by such elements. So this mi just the positive integers, and I is a finite subset of V. So it is easy to see that V is finitely strongly generated, means that this RV is finitely generated. So with this condition, so Tomoyuki proved that let V be a finitely strongly generated vertex algebra, then V is C2 cofinite if and only if the associative variety is a point. So that is very nice. So it's a geometric characterization of the C2 cofiniteness. So now we also note that this RV is a Poisson algebra. So this SV is a union of smooth analytic Poisson varieties. So this means that this SV is a union of symplectic leaves. So then defined by Tomoyuki and Kazuya, they defined that a vertex algebra V is called quasi-leaf. Is called quasi-leaf if this SV has only finitely many symplectic leaves. So I don't know if there is an algebraic definition about it. Okay, so, and they proved that if V is a quasi-leaf VOA, then V has only finitely many ordinary modules. So then you can consider the choice functions. So they proved that for any ordinary module, the choice function converges to a holomorphic function on the upper half plane. And so for more results on the associative variety of a VOA or VA, one can reference the following paper. I think I could miss some of them. So yeah, I'm sorry. Okay, now there is another geometric object for a given vertex of the algebra. That is the singular support of V. It is the spectrum of the associated graded algebra, GRV. It is with respect to the Hessian-Lee's canonical decreasing filtration, and this, which is a vertex Poisson scheme of infinite type. So for the study of this, I can refer the following paper. So I have read some, but I have to see that I understand very little. So here Li means Li, not Hessian Li, Li Hao and Hao Li, yeah, and Alton Millers and Hao and okay, their works. Okay. So we want to find another geometric objects for a given VOA, as I said in the motivation. So we start this. So let V let V be an ingrided V. So not necessary CFT type means that not necessary V0 is one dimensional. So then this RV is also ingrided. Okay, then we take a point in RV0 and the MX be a maximal ideal correspond to this X. So then we have a RV module CX, and then we can define the unit algebra. This we can define this algebra. Okay, define this. So this algebra, okay, I'm sorry. Oh. So this algebra is graded, but it is not graded contuitive in general. So if we consider we want to define some scheme or maximal ideal spectrum, so we have to do something more. So then we let this Rx be the set of all the two-sided ideals of this. And such that the quotient is commutative. And then we define a partial order by this. So such that I is bigger or equal to G if and only if this I contains in G. So this partial order is very natural. So then if this I is satisfied this, then we denote the natural projection by this and by this phi ij. So in this way, then we oh sorry. In this way, then we have a inverse system. This then we have an inverse system. Okay, have an inverse system. Sorry, have this. Oh, yeah. And so we can consider the inverse limit. This can consider this. So with this, then of course there is a natural form homomorphism of algebras of this. Okay, of this. Then with this we can define the scheme and the maximum spectrum. So now let V be an ingrided vertex algebra, and we have MX. Okay, as before. Then the cohomological scheme of V at X is defined as the scheme of the spectrum of this. On the spectrum of this. Okay. And the cohomological variety of V, this is the cohomological scheme here. The cohomological variety of V at S is defined as this, the maximal ideal spectrum of this. Okay. So that's the definition. Now, so let me give a brief remark. So if A equals RV, we know that it is not necessarily causal, but it is ingrided. And if this V0 is just C, that means that V is CFT type, then we have this. Then we have this. So therefore there is a duality between this RV and this. So this which suggests a dual in some V between S V tuta S V and this. So where S V tuta is the spectrum of RV. So that's one's motivation of us to consider this question. Okay. Now we have the following proposition. This proposition is not difficult to prove. So for an ingrided vertex algebra with mx, then we have this. So we have this. It is the union of this. Okay. And also we got some factorial properties of this. So now we introduce some notation. So now let V is the category of V is, and V FG is the category of finitely strongly generated V is, and the VOA FG is the category of finitely strongly generated V vertex operator algebras, and the T the category of algebraic varieties, and the S the category of affine scheme. Then and we define the factor the f theta from V to S, so V maps to its scheme. Okay, associated scheme, and this V associated maps to its associated variety, and oh sorry, I should do that. Okay, the third one is just V to the cohomological variety at X. Then we have the following proposition. So this maps F and F theta are contravariant functors. And the third one is a covariant functor. So that's the factorial one of the factorial properties. So another property we also get that letter V, V1, V2, VA, the vertex algebra in V, all this, and such that the following objects is well defined. So then for MX1, here, and MS2, then we deduce that we have this. So if we consider the direct sum, so the cohomological variety at X is if X equals S1, it's just the cohomological variety of V1 at S1. Similarly, if X equals S2, it's just the cohomological variety of V2 at S2. And for the scheme here means the scheme. For the variety, the cohomological variety, the result is similar here. So if we consider the tensor product, so then we get this. So the tensor product at S1 S2, the scheme is just so with the condition that RV1 is the local. And similarly, we have also this. Okay. Now, in order to determine or compute the cohomological variety, we needed to do things more general, because in general the cohomological variety to determine it is not easy. Sometimes it's very hard, I think. So now, this theorem is more generous. All we may see that it has nothing to do with VOAs. So now letter R is a ring like this. R is this. And suppose this C1, CR is the minimal set of generators of homogeneous elements of order of degree at 2. At least 2, not at 2, at least 2. And so then we can write this Cj in this way, right? Can write this. So then we get a surjective homomorphism of graded algebras. This. Then we get this. And this J is generated by elements such in this form. Okay. So I will not give the details of the proof. So it's quite long. It's quite, we need some lemmas, some other things. Okay. Then with this we can obtain corollary. So this corollary is helpful to for us to consider some examples such as affine view. So this corollary is that if we set R equals this, and as we have said that this C1 CR the minimal set of homogeneous of degrees. Here we at least three, not at least two. So then we can use that this scheme contains a closed affine space subspace AR. So with this we can do something about affine. We will see the examples below. Okay, so now because we obtained some general result from material properties or such. So we as I said, we wanted to find something which is due in some way to the associative variety of V. So we would like to see some examples. So next we can we just look at some examples. This. Okay, sorry. Okay. So the first example is we see that is the universal Virasoro VOA. So we just let VC0 be the universal Virasoro VOA, and this LC0 the simple Virasoro VOA. So with the central charge C respectively. So I think people are very familiar with this. Okay, so I will not give the detailed construction of this Virasoro VOA. Now, so for PQ, positive integer PQs, they are equal to 3 or more than 3, such that they are prime to each other. So we denote CPQ equal to 1 minus 6 P minus Q squared over PQ. Then we have the result given by Wang. So he proved that LC0 is rational if and only if C is. So we have talks before. So with rational means that the category of the admissible modules is semi-simple. So he proved that it's rational if and only if C equals to CPQ. So here rational is also C to cofinite. So and from the result we can get that if C is not equal to CPQ, then the coordinate range, the RV, the C2 algebra is just the polynomial algebra on X. So and if C equals CPQ, so it is a quotient by this ideal. It's a quotient by this ideal. So then it follows that this if C equals CPQ, then the associated variety is a point, and otherwise it is C, right? So then we can look at it's a cohomological variety. So then we have this. So the cohomological variety of the simple Virasoro vertex algebra is given by this. If C equals CPQ, it's just C. Otherwise, it is a point. So you can see it's the duality, the relation. So here just the opposite, right? Okay, then we can because this case is easy to determine. So now let's see another example. So let this VKG be the alpha vertex algebra. Of course, here G is a simple the simple finite dimensional the algebra. We'll see. Okay. So of course, with normalized by non-general bilinear form, then we have the affinization, then we have the Berman module, and from the trivial module of G, we get the Berman module. Then it has the VOA construction. That is called the universal alpha vertex algebra. So here I will not give the detailed construction. Okay. So it is well known that the C2 algebra is just the polynomial algebra over CG star over G star. So then it is obvious that the associated variety is just the G star in this case. Now let LKG will be the simple one, the simple alpha vertex algebra. Then the variety, we know that it is known that the variety is a Poisson subscheme of this G star, which is G invariant, and it is also conic, where G is the adjoint group of G. Okay, then so for this case, there are very nice results on this. So I can here give some. So okay, if K is equal to the negative dual cos number, then the shooting variety is just the nilpotent cone. So given by this in the cover. Okay, and also the shooting variety is a point if and only if LKG is integrable, as yesterday Tomoyuki also said that, also talk about that, and if only if this key is a positive integer. So but for other cases, so if K is admissible, then this proved by Tomoyuki that this the associative variety is a closure of nilpotent orbit in G. So in this case, the associative variety is contained in the nilpotent cone. So I want to give remark that there are cases when LKG is not admissible, but the shooting variety is still in the nilpotent cone. So you can see these two papers. And also there are cases where the shooting variety is neither G star and no contained in the nilpotent cone in G. So you can refer this paper. So anyway, in general, we give this the result. So that means that if the simple one is a non-trivial quotient of the universal one, then the shooting variety is a proper subvariety. Okay. So now we want to consider the cohomological variety of this, but we consider the simple case just as the K is a positive integer. Then we introduce this NK is this. We let NK is this. Okay. Oh, sorry. K and K is this. So the where theta is a positive has the has the root of g. Okay, so that AK actually it comes from the well-determined formula. So this NK is a polynomial in K. So then we have the following result. So this we prove that for the universal alpha will E. So because this case it is CFT type, so we just let x 0. So then we prove that it is a point. So we can see, remember we have that if we consider this, we call it is G star, right? So here it's just a point. So if k is a positive integer is equal to or bigger than 2, then there is a closed embedding of algebraic varieties. This. Okay, this. And and this the degree of this in K, because it is a polynomial of in K, so we can see the degree of it. But now we cannot determine completely the cohomological variety. We determine this by using the corollary we gave before. So we hope to get a better result on this, and we also want maybe to study some other examples. For example, lattice view, so we can find something maybe can the duality or to see more properties or relations to the associated variety of V. But for these two examples, we could see some relations. So and in the some kind of duality. So we know that for all the k positive integer k, the associated variety is just a point. But here we can see that the cohomological variety heavily depends on k. Okay.